Chapter 30, Electromagnetic Induction. Now, there's some fancy words. There's a lot going on here. But if you can get the basics of it, it's not that difficult to conceptualize what's occurring. The math we'll see, it's a little bit going to do with change. And of course, change is a what? Yes, that's correct. Who was it? Very good. That is a derivative, of course, and Angel, of course, got that. Thank you very much, Angel. But what we're going to do is, I'm going to look at induced currents a little bit, and then the next video after this will be on motional EMF, and that'll be all for this Wednesday. Induced currents. Faraday came up with this. I'll say it was discovered by Faraday. Around 1831, if I'm not mistaken. 1831. And I can do the history, but the history's nice. But let's give you something relevant. Now, there's a thing called a radio that you would have on. And if you listen to a radio, some of you might do that. Now, of course, when everything goes really, really bad, and there's a nuclear war, and then the electromagnetic pulse happen, and it knocks out a bunch of stuff. We're all sitting around listening to AM radios. And if you have an AM radio, you just happen to have your generator running, and so you turn the light off. Of course, I'm being a little facetious, of course. Go to your grandpa's house and listen to AM radio there. Just don't infect him with the coronavirus, okay? Your grandma or grandpa's house, they're sitting around listening to AM radio, and if a light switch goes on and off in that room, you may hear a little crackle on the AM radio. You're like, why did I hear a little crack, a little bit of noise or something when the light switch goes on and off? And I've heard it before. And you can demonstrate it. Why is that? What's going on there? Well, it's based on the idea of induced currents. And this idea is that when a current runs through a wire, it's creating a magnetic field. But then when the magnetic field changes, it tries to push electrons to cause it not to change. If you think about it, it goes back to the concept of inertia. Okay? It goes back to the idea of inertia. What's inertia? Well, as Thornburg rightly said, inertia, of course, is things want to keep doing what they're doing. And, object in motion wants to keep on moving. A B field wants to still be there. Space wants to stay bent, modified, changed by a field. And so it tries to stay that way. Things try to stay that way. And so if we want to look at an induced current, we got to think that for some reason the magnetic field, this idea of inertia, goes into fields. Fields like to stay constant. They don't like to change. And since fields don't like to change, and why, I have no clue. Ask the man upstairs. I'm not talking second floor either, Dr. Cook. Why do they want to change? I don't know, but they don't. And so what we're going to see is, I'll do a little demo here for you, is that when magnetic field changes, a voltage is caused. And of course, voltages induce, it pushes electrons. It causes a potential difference. So what I've got here, I've got a voltmeter. Pull the table up real close to you. Okay. And I've got a coil of wire. That's going to be one part of the coil of wire. There's the other part of the coil of wire. Oh. Okay. So let's attach this to it. Okay. There's this to one side. That's this to the other side. And we're going to put this on DC volts. And that's on the let's put it on the 200 millivolts. It's nice and sensitive. 200 millivolt scale. Now I'm going to take our magnets, real strong, one of those neodymium magnets, rare earth magnets, and what we're going to do, we're going to place it near this coil of wire. I use a coil of wire because it can be used to amplify the effects. I'll show you here in a minute. Well, on the next lecture, I'll show you don't even need a coil. It's lighter effect, but you don't need. But now this has got a metal base around and everything, so I can't really move it real fast inside here. But you'll see that as I move this magnet near the coil of wire, you get an induced current. Now if I keep it still, nut and honey, right? The old cereal, nut and honey. Nothing on there, right? Now if I move it, you see a little bit of induced current. Excuse me, voltage there. Of course, that voltage induces a current. Now if I fast, move it real fast, gotta have sound effects, right? If I do that, I'm having way too much fun. You get a greater induced voltage on there. Of course, this is millivolts, but you can say, 4 or 5, maybe 10, 12, 15 when I was messing around earlier, I got. So there's an induced voltage with this. Now, you say, well, I'm just moving a magnet. What if I keep the magnet still, and move the coil of wire? That works as well. It's not just a magnet moving. If I want to generate electricity, I can move magnets, or I can move coils of wire. And of course, generators would never do that, right? All right, so I can do that. Of course, let me take this off here. It could be like that one guy, supposed physicist, astrophysicist in England that stuck 2 magnets up his nose because he was doing coronavirus research. No, he was just stoned, probably. I don't know. I'm just saying. Now, if I have just one, it's a lesser effect. You'll see some, but not as much. Okay. But there you go. All right. So what I have hopefully demonstrated to you is induced potential that would actually cause a current. So what I will say is, what Faraday found, that when the magnetic field through a coil changes, induced current is produced in the wire. I don't think produced is the best word, but I think it gets the point across. So if you have a coil of wire, and then you put a voltmeter across it, let's change this to be induced potential. Let's just be correct, since this is going on YouTube and somebody will make some snarky comment later on. Ooh, that's not right. You're wrong. You don't know what you're talking about. Is created in the wire. Okay. So if I keep my magnet still, here's my magnet. If it's still here, of course, the magnetic field is coming out doing this. And of course, some of it goes through the coils. But the key is, it's got to change. So when there's motion, the field lines going through the coil change. And when that happens, you have an induced potential, which causes an induced current. Okay? Now, this could be a magnet. This could also be another coil of wire with current running through it. And that's the case of what I talked about with the light switch. If I have another coil of wire with current running through it and I flip it off, then all of a sudden the magnetic field here, which was strong, or at least somewhat strong, goes down to nothing. And part of this magnetic field, if I replace this with a coil of wire, this field now is gone. So this number of field lines that cut through there would change. And if the number changes, you induce a potential which causes a current. That's how that little staticky you hear on a radio when you flip the lights on.